Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. It's my great pleasure to introduce Parag Agrawal from Stanford University. He's been working in a wide range of areas. The main thrust of his work is on probabilistic and uncertain data, but he's also been working on data cleaning, namely indexing, containment of data, but also things like secondary index maintenance and distributed systems, and even something as far-fetched as blog ranking. So if you meet with him later, feel free to ask him about any of these areas. And other than that, I'll hand it over to Parag.
Thanks, Vishen, for the introduction. He already finished off 2 of my slides, so please forgive the repetition. So as Christian said, I'm going to talk about the title of the talk is Coping with Uncertain Data. I'll talk about some of my thesis work, which is all about uncertain data. And then I'll talk about some work I did here at Microsoft Research with Raghav and Arvind, which was about indexing error-tolerant set containment, but it has challenges. One of the challenges comes out of dealing with uncertainty. Okay? So as Christian also mentioned, I did a bunch of other things. I'll try to give you some introduction to some of those things, like 1-slide overviews or like 1 bullet overviews to promote talking about those things in my one-on-ones. So let's get started with uncertain data. Let me start with an example and tell you what uncertain data is or uncertain databases are. So let's say I wanted to extract dates of 2010 World Series games, and let's say for the sake of PowerPoint that there are only 3 games in a World Series game. So I suppose have a Wikipedia article that I want to extract from, and I write a very, very naive date extractor. It's not smart, it's not optimized, and it just finds 2 dates for me and nothing else. It doesn't tell you which game is when or any such information. So at this point, if I think about it, this could mean that game 1 and game 2 are on October 28th and 30th by knowing these 2 dates. But it could also mean that game 1 is on 28th and game 3 is on 30th, or it could mean that game 2 and 3 are on 28th and 30th. Notice that I've used some knowledge here in generating these alternatives or possibilities, which is that game 1 is before game 2, which is before game 3, right? And I've also sort of implicitly assumed that these dates are associated with at least one game, and that games are on distinct dates. So based on all this knowledge, I've sort of conceptually created what we call possible worlds. So we have 3 possible worlds listed here for a database which was about games and their dates. So this, I'd argue, these yellow 3 tables, yellow tables are 3 possible worlds of an uncertain database. So intuitively, an uncertain database consists of possible world, and the intuitive meaning is that the real state of the database is one of these possible worlds. Okay? Let's move on. Another way uncertain data can be created is through sensors. And let's assume we have like 3 rooms, and we have a sensor, let's say the blue sensor, which can sense some part of room 1, room A and room B. Okay? And the sensing is of the form that if there's an object within the shaded blue area of room A or room B, this sensor is going to read its ID. So suppose this sensor reads an ID. At this point, it reads the ID object 2. So it knows that the object 2 is in this blue shaded area. So it has to be either in room A or in room B. So it's created conceptually this uncertain database, which is room A or room B. Similarly, suppose there was this other sensor, the yellow sensor, which now again detected object 2. This again reports an uncertain database which says the object 2 is in room B or room C. At this point, knowing what the sensors do, we know that the object has to be in this light green area because it's detected by both of the sensors. Also notice that this color scheme will sort of go through the talk, that blue and yellow combine to form green. So at this point, by combining information from both of these sensors or doing data integration in some sense, we should be able to conclude that the object is in room B. Okay? So here what we have conceptually done for this example, we have done some reasoning with uncertainty and sort of resolved or removed the uncertainty. Okay? And this will be a theme during the first part of the talk. Another kind of uncertainty which is very different is that data has non-canonical representations. So here the motivating example I'm talking about is we have a venue and their names, but people refer to these names using different ways or different representations. A user could refer to square as SQ and New York as NY. So due to this non-canonical representations, what we conceptually have is multiple names for the same venue. And there could be a very large number of them if there are more such non-canonical representations, in fact an exponentially large number of them. One of the challenges this introduces, in this case the motivating example was just searching these names, is one of efficiency. How do we do efficient search in the presence of this large exponential explosion? And the second part of the talk will sort of deal with this challenge, and I'll get into more details there. So with this, the talk outline is, in the first part of the talk we'll talk about data integration, which was about reasoning with uncertainty as we saw in one of the slides. The second part will be to deal with efficient fuzzy lookups, which is work I did at Microsoft Research with Raghav and Arvind. And then I'll just have one slide overviews of some work I've done on trendy topics to promote discussions. So what's an uncertain database? Revisiting that. As I mentioned, uncertain database is essentially a collection of possible worlds. So I'm not talking about uncertain databases with probabilities for this talk. I'm focusing on uncertain database as a set of possible worlds. Probabilistic databases typically are these possible worlds with a probability distribution over them. And I'm not going to get there during this talk. So think of uncertain databases as sets of possible worlds. Now what are the semantics of queries over uncertain databases? When a query is issued, it essentially in concept is issued over each possible world. The answer is created as a possible world of the result. So the result is also an uncertain database, which is a set of possible worlds. So conceptually the query is applied to each possible world and you get an uncertain database as a result. So this is the semantic layer, never actually done in practice. What you'd have is the set of possible worlds can be very large. These are represented using a compact representation. Think of the non-canonical slide, wherein I essentially said by storing just how user might refer to square, SQ to square, that's a compact representation of a large number of possible worlds. So you'd have a compact representation for an uncertain database. Query processing now involves getting a compact representation of the result without ever expanding out to the possible worlds. So this is the efficiency part, and this is what, so the bottom part is what a typical uncertain database implements, and the upper part defines what they want to implement or the semantics for it. Okay? So what are applications of uncertain databases? I mentioned sensors, which is a commonly used application. Extraction is another important application because it generates a lot of uncertain data. Scientific data is another place where a lot of uncertainty occurs, and the process of data integration, because you might not know schema mappings, you might not know exact results for entity matching. So, but one thing you can observe in all these applications is that there's often not only one source of data, the blue source, but also other sources like the yellow and red source. For example, you could have multiple sensors which are reporting partially overlapping values. You can have multiple extractors on the same web page. You can have multiple web pages which are talking about the same information. So you'd conceptually like to be able to combine information from all of these. And each source essentially is an uncertain database. Okay? So in scientific data as well, you could have multiple experiments or multiple observations supporting the same hypothesis. So one common theme, and data integration by definition has multiple sources. So one common theme is that in a lot of applications of uncertain data is that you have multiple sources of information, all of which could be uncertain. So that's sort of what we'll handle in this talk. I forgot to mention, please stop me at any point to ask questions, clarifications, anything. So let's move on with this motivation to talk about uncertain data integration. So let's again try to draw the same picture. What would uncertain data integration look like? So what we have is a collection of uncertain databases, the yellow, the blue and the red, and maybe more. In typical data integration fashion, we'd like to have a unified query interface for querying information from all of these sources, which would be our mediated schema. We'll need a bunch of mappings to associate each database with the mediated schema. This is just standard data integration applied to the uncertain context. And now one question is, when a query is issued to this mediated schema, what should the result be? Okay, so this is one thing we'll talk about during this talk. The second part, which is how do we compactly represent these uncertain databases? How do we efficiently do query processing over these compact representations to get a result representation? This is something I will not discuss in this talk, but we have some work in our papers about this. So what I'll do is focus on the upper part, defining what should be the results of uncertain data integration. Okay, so this will be primarily theory and definitions. The second part will be more applied. Okay, so let's take a step back and see what data integration typically looks like and the high level objective. In a very simplistic world, I have two certain tables, the blue table and the yellow table, and I'm trying to combine them. So intuitively what I want to do is get their union in some sense. So here what I'm trying to show is the green part is tuples that occur in both databases, and the yellow part is tuples that are only in the yellow database, and similarly for the blue part. So what we've gotten is more data as a result of data integration. So notice that I've assumed sort of that both of these are in the same schema, their identity mappings and everything, but intuitively we get more data as a result of data integration. In the uncertain world, what we have is we're starting with two sets of possible worlds, two uncertain databases, and we're trying to combine them. What I'm going to argue is that you're going to get more data, but you're also going to get less uncertainty as a result of this combination, as we saw in our motivating example about getting the certain result for where the sensor was. So this will be a theme in the talk, how to get less uncertainty. How do we make this happen? So again, one intuition that sure.
Why do you say it's only less uncertainty? How do you know it's not going to be more uncertain after you get, say, two readings?
So that's a very good question. So it's not always less uncertainty. For instance, if you have two databases which are totally unrelated with each other, that is, we cannot correlate the possible world of one with the other, or it tells you that there's absolutely no overlap in them. That means when we combine them, you're not going to get any less uncertainty. So more and less uncertainty is sort of ill-defined at the moment, right? So one way to think about it, in this context of knowing about the same data, the fewer possible worlds there are, the more certainty there is. But that is in the context of the same data. If you get information about 100 more tuples, counting just doesn't do it. Okay? So let's now revisit the extraction example. So what we had was, we had one extractor which gave us two dates, 28th and 30th. And from that we created this uncertain data with all those assumptions I spoke about. Suppose we have another extractor which gives two other dates, okay, 27th and 28th. At this point, this also has an associated uncertain database. So what we'd like to do is combine these two uncertain databases to achieve this result, which is at this point, based on our assumptions, the truth. Because if you reason yourself, it's like we totally know now three dates from this. We have the assumption that all of these dates are associated with games. We also know that these games are on distinct dates, and game 1 is before game 2, which is before game 3. So you can reason your way to saying that, okay, this should be my result. And so the way you would get this from our uncertain databases is that two of the possible worlds are agreeing with each other on the game 2 dates, and the other possible worlds are contradicted by information in the other possible world, in the other database. Okay, so we essentially want to formalize the intuitive reasoning you did to create this certain result. We'd like to formalize it in terms of data integration over possible worlds. Okay, so let's move on. So the setting we'll be thinking about our data integration problem will be the local as view setting. So what the local as view setting means is, you have a collection of sources and a mediated schema, which is the unified query interface. And the way the mappings are defined between these sources and the schema is what's called local as view. So you can think of each of the source as being a view over the actual database. So the mediated database is the actual database. Each of these sources is defined by a query QI, which is a view over this database. And the constraint is that the mediated database or the actual database should contain at least all of the information in the view. And hence each of the sources is a view of this mediated schema. What this implies is that M has to be such that it has enough data to such that when queries are issued over this, you recover your views and maybe more. Okay, so let's see how this works in the certain data case. Again, we have the blue and the yellow database. You combine them. These constraints are satisfied by this M called M1, which is essentially the union, as I said before, plus one extra tuple, red, which is not in any of our sources. This satisfies the local as view mappings. So this is a valid mediated database. Okay. Similarly, there could be others which have some other red tuples. Okay. But among them, there is this one, which is exactly the union, which is in some sense the least informative of all valid mediated databases, which does not have any information which is not implied by one of our sources. Okay. And that's essentially the definition. So I did it in terms of the unions, but you can apply the same argument over queries, over mediated schema databases. So essentially the set of certain answers, as has been defined in data integration, is the least informative answers from a valid mediated database. Yes?
So what if I added a possible world in which there's a fourth date introduced, so that if you backed up to the previous slide, you would just have another possible world in there. And now there really isn't going to be a certain answer that I believe that's going to be covered by all of them. Then does that mean data integration is dead?
No, so we are actually, so if you had uncertainty of the form that there are 4 dates and only 3 real games, conceptually, so the answer then at this point, given our state of knowledge, is an uncertain database. And that is the need for doing uncertain data integration. So for instance, to go to our example, actually, let me try to rewind there a little bit, sorry. Oh.
No, I got it.
Oh, okay, was it clear, or I can explain more? Sorry about this. Yeah, so suppose these 2 sensors had now reported, let's say, completely different dates. That guy had reported, say, 29 and 31, okay? But we've sort of currently used the reasoning that all of these dates are correct. So we haven't created a possible world saying that 28 may not be the date for any of the games. In which case, having these 2 sources will in some sense become inconsistent, which will come up later in the talk. But now, if we had reasoned that some of these games, if we had allowed that the possibility that, okay, maybe these dates don't correspond to any games, in which case an empty database here, and the databases with just singletons, that game 1 is on 28, or game 2 is on 28, or game 1 is on, or game 3 is on 28, and we had created all of these possible worlds, in which case when you combine them, you'd essentially get sort of the intuitive database, intuitive answer you'd like, which is that there are these 4 dates, in some order, in some permutation, some 3 of them correspond to game 1, 2 and 3. That's what would happen as a result of what we do. But that's a very good question, thanks. So moving on, in the certain case, we said that we have this notion of certain answers, which is the least informative of all valid mediated database answers. Yes?
I have a small question which I don't understand. Is it SI subset of QI of M, or you apply that on, is it QI of SI subset of QI of M?
So it is SI is subset of QI of M. So think of it this way. These are constraints for the mediated schema. It's local as view. So that what you're thinking of is global as view. Because the global is now, you tell us how the global mediated database, you can add information from the source. Here what we are saying is putting constraints on the mediated database such that it has to have enough data to satisfy these mappings. Okay? So, and this example essentially tries to show that anything which has all the blue tuples is allowed. So the QI in this example is I, identity. Okay? So this is what the certain data world is. Yes?
Query Q post on the mediated schema?
Yes, this is the query posed on the mediated schema, and we'd like to define what the answer for that is. Okay? Now conceptually, according to these mappings, any M is valid as long as it contains essentially all your sources, if you think of identity mappings. Okay? So all of M1, M2 and M3 are valid mediated databases. Okay? So now the semantics of the query are that answers which are in all of these. So in the certain case, this boils down to saying the least informative answer from all valid mediated database in concept is a certain answer. Okay? So that's what the notion of certain answers is. And now we are going to try to find the corresponding notion in the uncertain case. Define what the result is. What do these mappings mean? That's where we are going. Okay? So the key here that I'd like to point out is this definition of containment. So where have we used containment? We've used containment in defining what these mappings mean. We've used containment in defining, in defining what least informative is. So conceptually, in this certain case, we know what the definition of containment is. If all tuples from database 1 are contained in the other, it's contained in the other, right? And the same intuitive notion we have in our mind is what we've used in defining what these mappings mean in terms of what's a more informative mediated database than all your sources, and which is the least informative among all mediated databases. So what we'll essentially try to do is define a containment definition for uncertain databases which captures the notion of information or more informative than, to then achieve the corresponding definition of what these mappings mean and what the certain answer is, corresponding notion. Okay? So the key is this definition of containment. So let me now formalize what I mean by an uncertain database so that I can move on to defining containment for these. So an uncertain database consists of two parts. One is the tuple set. Intuitively, the tuple set is the collection of tuples that this database is aware of. A database is, we are in the open world assumption, so it does not know about all the tuples in the world. It knows about some slice of the world. Okay? So that's the tuple set T shown here in light blue. So it knows about, say, the object 2, rooms A and B, and its possibility of being there. And there's a second part which is the set of possible worlds. Within these tuples, it knows that here are the possible worlds for this tuples. So each possible world is a part of the tuple set, and in this example W1 and W2 essentially say that one possible world is the object 2 is in world A, in room A, and the other is object 2 is in room B. Here the information it is telling us is that object 2 is in at least one of these two rooms, because if it did not have that information, it would have added the empty database as a possible world. It is also telling us that the object 2 is not simultaneously both in room A and room B, because if that was the case, it would have added another possible world which had both of these tuples. Okay? So its information comes by not enumerating some possible worlds. So think of now a degenerate case, which is suppose the possible world set was just the power set of T, so all combinations, in which case this database is really giving us no information. It essentially says no answer on every bit of information you can ask it. I don't know whether this happens, I don't know whether these two happen together, I just don't know anything. So this is the no information case. Second is, again, to stress that absence of, okay, so suppose now a tuple set contained a third tuple 3p, is the object 3 in room P, did that event happen? Now suppose I keep the possible worlds the same and the tuple set is now increased. So now what it's saying is 3p does not occur in any possible world. So an absence of a tuple in a possible world is also information, because here it's saying that the object 3 cannot be in room P. It has somehow extensively looked at room P and determined that object 3 is not in there. So absence of a tuple in possible worlds is also information. Okay? With that intuition, let's move forward. Now let's try to define containment in one degenerate case, which is what if our uncertain database had only one possible world. This sounds incredibly like a certain database, but with the twist of that absence of information is also information. Absence of a tuple is also information. So think of the example. Let's say we have an uncertain database U1, and its tuple set is this light set of tuples. Since it's only one possible world, I can show it using this representation. The dark ones are the ones present in the world W1, while the tuple set is the entire thing. So in some sense it's saying that the light tuples here are not present in the database. Okay? So that's the information here. Suppose we had similarly a second database, the blue one. Yes?
How do you go from your tuple set to the possible worlds? Who gives you that mapping? You are saying assume single possible world.
Yes.
Or it could be no information, or it could be that an object is only one of these two rooms.
So in our extractor, so you can think of it this way.
The extractor will tell you some measure of...
The extractor essentially tells you, so typically what will happen is the extractor will enumerate the set of possible worlds for you. And hence, any tuple that occurs in any of these possible worlds is definitely in your tuple set. But there may be more. Think of it this way. In the base data or in original relations, we may not encounter scenarios where an extractor explicitly gives you negative information, which is of the form that, okay, this event just did not happen. But when we start combining these uncertain databases, and we get a resulting uncertain database, we were able to eliminate that the object 2 is in room A. We'd now like to capture it, because by combining information we can get two negative information, even if we started with no negative information. Okay? So to keep our model complete in terms of incorporating results of combination of uncertain databases and keep that within the world of uncertain databases, we need to be able to represent such negative information in our definition of uncertain database. Okay? But you can also imagine that these sources do tell you about negative results. Think of it this way. Suppose I created a source slightly smartly. So I have a sensor which completely records information for 2 rooms. Okay? I know I do not detect the object 2 there. Okay, so it can now insist that the object 2 is not in room A and it's not in room B. Okay, this can be information that an uncertain database corresponding to this sensor can report. Okay, so now again to go back to this slide, we're in the world of single possible world databases. The light tuples are ones where this database is asserting that these tuples are not present in the database. The dark ones are ones where it's asserting that these are present in the database, and we are trying to figure out whether U1 is contained in U2. So the definition here is kind of trivial, right? That you want to make sure that for everything that U1 knows about, which is definitely contained, U2 must know about it. So in terms of presence of tuples, U2 should have more information than U1. Similarly, in terms of absence of tuples, U2 should have more information than U1. Okay, if these things are satisfied, U1 is said to be contained in U2. So this is just a minor extension to the containment definition for regular databases, incorporating this absence of tuple information. Okay, so now let's try to generalize this to sets of possible worlds. Okay, so again we have these two uncertain databases, the red and the blue. We are trying to figure out whether blue uncertain database has more information than the red uncertain database. Intuitively recall, fewer possible worlds are more information. Okay, so to do this, what we are going to say is, for all worlds in U2, for each possible world in U2, does there exist a possible, can we find a possible world in U1 such that the single possible world definition that we had previously applies. Okay, so basically what it's saying is that we don't need a possible world for all red possible worlds to be represented in the blue one, because the blue one is allowed to be more certain. It is allowed to eliminate possibilities from the red world, right? But the blue one, for everything in the blue one, it should be allowed by the red database. The red database is not allowed to contradict any of that or give additional information there. Okay, so for every blue database, we would like a possible world in this blue database to be there to be a corresponding one in the red database, so that there is this containment, which says that this blue one is more informative in that it is able to eliminate some of the possible worlds of the red database, but it contains all the information in the other one, the ones which it allows, and is bigger than that. Okay, so that's the definition for containment for uncertain databases, explained intuitively. For people familiar with power domains, this is essentially a Smythe lifting of the single possible world containment definition. Okay, so the key changes we have made from going from regular databases is, we said absence of tuples is information in the context of uncertain databases. So that intuition was presented to create a definition for single possible world databases, and then we said that fewer possible worlds are more information, and hence we used the Smythe lifting to find a containment definition for uncertain databases. Okay, now let's see how this definition takes us to data integration. So again we have the same setup, the LAV setup. We have LAV mappings from sources to the mediated schema. We have, for this example, now two sources, each of which is uncertain, the blue and the yellow. A possible mediated database is by combining two individual possible worlds and adding some junk tuples as before, the red ones. Similarly, there could be another such database which is satisfied. So these arrows correspond to containment, that this M2, which is an uncertain database, again a single possible or uncertain database, that contains the entire source S1, and it also contains the possible world demonstrated for that, the corresponding possible world for S1. So now you could have many such ones, but you could also have uncertain databases which contain both of these. Hence the query result can be uncertain as a result of data integration, as we observed before. Again, there will be a least informative valid mediated database, and we show in the paper a result which says that there is a unique such answer to every query. So given a definition of containment which is a partial order, this minima may not always be unique. For the definition I have presented, there is a unique minimal which is what we will call the strongest correct answer. So notice again that we've used the definition of containment in two parts. One, we have used it to define what valid mediated databases are, and we've used it to define which one of these is the least informative one, and we can show that the least informative one is unique. So now that is the query result you would like. as a result of data integration. Okay?
Least informative one?
Yes. So think of it this way. The valid mediated databases is the set of databases which the mappings constrain to be more informative than each of your sources. There's a lot of such databases. But some of these databases will have information that is not implied by any of your sources, which are these red tuples, which is just junk in some sense, that none of your sources tell you this information, but the mapping still permitted as a valid mediated database. Okay? So you have this large set, some of which are more informative than any of your sources. Among these, you want the least informative one as your answer, just like the intuition for certain answers. And that's what we call the strongest correct answer in this case. And it's the corresponding notion to certain answers for uncertain data integration.
I wouldn't call it necessarily the least informative. You want the smallest database that contains
Yes, the smallest
sources.
database. Yeah. Yes.
So you go back to the certain world. So your query answer, you don't require a single instance of the mediated database, right? There are multiple possible mediated databases which satisfy your constraints.
Yes.
For a given query, you want the intersection of the result over all these,
In some sense, yes.
right? That is the
Yes.
only sense.
Yes.
So, so here now what you're talking about is you're saying there are multiple possible uncertain databases, and what does it mean to even say you want the query result over all of these? What does that mean?
The intersection, right?
You want the intersection. So for the
In some sense. So
query result on any one of these databases is an uncertain database,
yes.
and the query result on and so on. So you have a bunch of uncertain databases as a query result. What does it mean to even intersect uncertain databases?
Okay, so think of the intersection operation in the certain world as the operation which is that take the containment defined according to just set containment for tuples. Okay, intersection gives you the unique minimal set that is contained in all of your answers. That is the intersection operation, right? So the corresponding operation here is we have a containment definition for uncertain databases. You have a bunch of answers which are all uncertain databases. A set or a database contained in each of these is the intersection operation. So you've taken the intersection operation, defined it according to a partial order.
Strongest correct answer, you're saying the intersection is well defined. There exists a unique intersection.
Yes, it's well defined. Exactly.
And the main difference is the negative tuples.
What?
Compared to the other case, the main difference is you're accounting for the negative tuples. Is that right?
No, so there's two differences. So when you degenerate this stuff to single possible world databases, the difference is negative, is uncertain databases. But the Smythe lifting is the second part. So there's two ingredients. Knowing that uncertain databases can have information about tuples not existing. Two, that you essentially, less possible worlds is more information. And these two form together to form this containment definition, which can form the core of the entire semantics for uncertain data integration. Okay? So, yes.
You said there's a unique database?
There's a unique uncertain database.
There's a unique uncertain database.
Yes.
Which, in an uncertain database, is that a single world or is that a distribution over possible worlds?
It is a collection of possible worlds. So in this case, M4 is our unique. So let's say our mappings were identity and our query was identity for this example, in which case M4 would be the unique answer we would present, which is an uncertain database. But okay, great. So I'll move on. One question which I alluded to earlier in response to a question was that you can get inconsistency. How does that happen? Think of the two uncertain databases, the red one and the blue one. A and B are just tuples. The red database asserts that A and B are mutually exclusive. They do not occur together in any world because it presumably knows about both of them and does not allow the A-B possible world. Similarly, the blue database asserts that A and B always occur together. So if A occurs, B has to occur. If B occurs, A has to occur. These two pieces of information are conceptually inconsistent. There can be no state of the world where both of these things are true. And hence no uncertain database, according to our definition, can contain both of these uncertain databases. Hence we'll say this set of sources is now inconsistent. So the definition of consistency, which is fairly natural, is does there exist a mediated database which satisfies all your sources and all your mappings? Okay, so that's what the definition of consistency is. And this is an example where databases may not be consistent.
So these are sources? Yes,
Yes, the red and blue are sources.
And So why couldn't I have a distribution over possible worlds? So what is it? So every possible world in the mediated schema has to contain both of them? Is that the problem?
No, so the problem will be that, so think of an uncertain database. If it has to contain information from the red database, it has to say things like, it knows for the first possible world of it, A and B, it knows about A and B. So it has to have, according to the single possible world definition, that A exists and B does not exist. It has to have a world. So for all of its world, it has to have this information that B does not exist when A exists. Okay?
So every possible world has to be consistent
with this bit of
sources,
information.
and
Yes.
there's no possible world that can be consistent with these two sources.
Yes. So with these two sources, there exists no uncertain database. Okay. Thanks for that question. So now, this naturally leads us to the first question, which is, how do we check whether a collection of sources is consistent? So the problem concretely defined is, you're given a collection of sources, you're given their mediated schema, and you're given a bunch of mappings. The first question is, without even having any queries over the mediated schema, are these sources consistent with each other? So it's easy to see that this problem is NP hard. Another observation you can make is, it's p time when there's a constant number of sources. So the hardness comes from a large number of sources. Okay? But a collection of our applications were of the form that extraction, and we said that each extractor over each web page could be an uncertain database. So we'd like to be able to handle larger number of sources. So this hardness result is in some sense bad for us. So the hardness is not in the size of each uncertain database, but in the number of uncertain databases. Okay? We also have another p-time result which says that whenever these sources induce acyclic hypergraphs, and I'm not going into how hypergraphs are induced from sources, but I'm happy to answer that in more time when we have it, we can show that they're p-time. Okay? So these are just a collection of theory results to set up the problem. Yes?
Let's take an example of extraction. I'm just wondering why local as views, nobody does local as view, right? You can't, what they do is they typically extract the relational database from the document and then they just run SQL queries on it, which is the global as view. Produce the mediated databases, single instance of mediated databases, and run query answering. So why is local as view interesting?
So I think, okay, so there's two answers to that. One, local as view in itself may not be very interesting, but the containment definition is not restricted to in its application to local as view. The containment definition guides us in doing global as view as well. We just haven't nailed the details there. Okay. Second, local as view is interesting when you don't want to materialize the mediated database. So, and the reason for it being interesting more so in the context of uncertain databases is that you have a collection of sources, each of which has their representation. So notice how in uncertain databases a set of possible worlds is this union operation of just putting things in may not computationally be feasible or efficient. It might computationally be helpful to think of not creating this mediated database and deferring this uncertainty reasoning, which is the hard part, for the query answering part, to do it on demand only when required.
But can you give a little bit of insight on what at least the class of queries can support? As far as I understand, even the definition of intersection, you probably support only a very restricted class of queries, right?
So yeah, we cannot do aggregates, for sure. So uncertain, monotonic queries basically. So what we are talking about for mappings and for answering queries are monotonic queries.
For mappings, I can assume that that's a reasonable restriction.
Right. But we sort of, our definitions break when you don't have monotonic queries. So because certain answers now becomes trickier to define, the definition will break. So that's correct. If there are no more questions, I'll move on. So there's a collection, there's a paper with some interesting theory results, which if people are interested, they can look at. I'm going to conclude this part of the talk and move on to the second part. So I'll just tell you what else is interesting here. This slide essentially says how much we understand for, like the darker things are, the more we understand about how to do it. Lighter things are we don't. So we know how to, so we said in the talk I always kept identity mappings and very simple things. So, but we can do multiple tables and monotonic queries, we understand how to do those. we know how to do some things with efficient representation, how to do efficient query answering for this restricted cases. When we start adding probabilities, we have some ideas and we are writing those up in a new paper. And the idea is essentially at a high level to think of each uncertain database is essentially a belief function from evidence theory. So belief functions are some generalization of probability functions which let you express ignorance. And I'm happy to talk more about this stuff later. But this is very important because each of our uncertain database is ignorant in many ways. It does not know about certain tuples, it does not know complete information. So that's sort of why we went the belief function path in the context of uncertain data integration. And using that now we can do interesting things like represent non-reliability of sources which can be thought of as ignorance. Okay, we can do things like now the consistency of sources is not partial. Up till now it was absolute 0, 1 without probabilities. With probabilities only in some probability or some mass are sources inconsistent. So you get this partial inconsistency. Then you can also think about when you have probabilities, these sources may be dependent or independent, the way these probabilities are, and you need to reason differently. This is something we understand less. We have not gone beyond localist view. We have not even thought of an implementation because this is all foundational stuff to figure out how it can be done, the uncertain data integration problem. What you'd want to implement eventually is like a specific application of it rather than a general system. So I just want to mention quickly a lot of related work has happened in the uncertain databases world, in the world of data integration which we leveraged, in even some work about how uncertainty is introduced during data integration and what you do with it. One interesting insight was that uncertain data integration is useful even if you have certain data and uncertain mappings. Our definitions still apply, they give the correct answers. So that was an observation made in another paper which was talking about data integration and uncertainty. There's been work on data exchange in the uncertain case. We're leveraging evidence theory now quite deeply, and there's a lot more work which has gone into and contributed to what we did. So we finished like one part of the talk, which is the theory part. Yes?
Are there extractors that will give you probabilities in their answers, or is
they give you scores? You can get scores everywhere. You cannot get probabilities. The only place where we know that you can get probabilities is if you're using, for instance, if you're using some sort of a forecaster, saying that we have this parameterization for forecasting sales in this region versus what will our sales be. So people will probabilistic models to do this forecasting. So for real world events, the data you get are usually scores. You can sort of mush them into probabilities or find probabilities any way you like, but for forecasting, it's more easier to think of the data you're getting as probabilities.
Is there value in interpreting scores or these pseudo probabilities derived from scores in order to do the kind of inferencing you're doing on certain data? Is there any reason to believe that would be a useful thing to do?
So that's a nice question for philosophical argument, but let me just give you a very short answer on that. If you have exactly one number associated with each event, Cook's theorem says that treating that as probabilities is the only correct way of doing it if you want certain nice properties. There's this very old theorem, Cook's theorem, which is the justification of all of probability theory, saying that if you are allowed only one number as score to represent certain information about these events, and you want to do reasoning on that, probability theory is the only way which has all these properties which are natural and you'd want them. Okay? So that's sort of the argument saying that why you should try to get anything you have. If you are going to do anything with it, somehow bring them into the world of probabilities and then deal with them. How to do that is the hard part, and no one has sort of answered it. Okay? So I'm really running low on time, so I'll quickly move on to the second part, which hopefully you'll find interesting as well. I'm going to rush through this part a little bit because I'm low on time, so please interrupt me when I'm too fast.
An hour.
Yeah. So don't worry, we can go up to 12.
Okay, great. So I'll not. So fuzzy lookups is the topic of the second part. I said, so I skipped through this slide. The challenge here will be dealing with efficiency in the presence of uncertainty. So think of this part as the bottom part of this, that will define the semantics, which was the top part in our possible worlds a priori, and try to see how we can represent and efficiently execute those semantics for efficiency in the lower part, in the possible world part. So fuzzy lookups is the topic of this part of the talk. Our motivating applications were record matching and local search for fuzzy lookups. So in general, fuzzy lookups are essentially based on a similarities function. So you have this large reference relation and you're trying to look up tuples which are similar to a target query. The reason they're fuzzy is they want to permit error tolerance. You want the query may not be exact match as equality match, which you could do using a simple hash table. And various similarity functions are used to this end. Commonly edit distance, Jaccard similarity, Winkler distance, so on. The motivating applications we had for this were in the context of record matching. So in a data cleaning platform, you might want to do data cleaning and entity resolution. So as a first cut to find candidates for things which might be the same record, you want to do efficient lookups rather than doing pairwise comparisons across everywhere. In another motivating application is local search. So in both of these applications, we are thinking about conceptually small records. So we are not searching documents, we are searching records, okay, and this will become important later. So another key to this is that there's various similarity functions which are useful in various contexts, but if you think of set similarity based lookups, like say Jaccard similarity, they can form a primitive function for executing multiple such similarity functions, for instance, and that's why in a data platform, in a data cleaning platform, or as a generic primitive, set similarity functions are more interesting, and this was something identified in previous work. So now we are going to use the set based similarity method called Jaccard containment, and let me try to define what it is. There's a bunch of you here who know this part, so please be patient. So set containment is what regular keyword search is thought of, that you have a reference relation, think of a record in a reference relation R, and you have a query. It's in the result if the entire query is contained in your document. So if all the words in your document are in the query, it's the set containment based lookup. In this case, we have an additional word called pasta. Suppose we also have weights. So now Jaccard containment is defined as how much is what fraction of the query is covered by the record. Okay, so think of, in this case, the word pasta is not in a record Olive Garden. So the total weight, so these are not probabilities, although they sum to 1 for convenience. They sum to 1, the weights, and 0.8 is in the record. So 0.8 fraction of the query is covered by this record. Hence the Jaccard containment is 0.8. Okay? So another way to think about this is an asymmetric version of Jaccard similarity, because we are now penalizing only by the size of the query, not by the size of the union. Okay? So we are not penalizing for large records in the reference relation in doing our similarity. So the problem of fuzzy lookups is to efficiently find all records such that the Jaccard containment value is beyond the threshold. So that's our lookup problem. Okay? Now let me introduce some uncertainty into it. So we know that users sometimes abbreviate square as SQ, New York as NY, and make countless other ways of other mistakes. So what we conceptually have, let's say, is a collection of transformations like these, which say that square, when a user says square, he might mean square. So one way to think about it is that the name is uncertain, and that we'd like to make all of these names, which are just representations of this name, knowing what kind of other representation the user uses, as searchable. So we'd like these 4 possible worlds in some sense to be searchable. And now when we define Jaccard containment, we would like to define it as the maximum Jaccard containment over all possible worlds. So the Jaccard containment for this venue is over all possible worlds the maximum value, which is the max match. Okay? So this is the semantics we are attacking, that you would like the max Jaccard containment over all possible worlds to exceed a threshold. Okay? The challenge is efficiently processing this without actually creating all of these large number of possible worlds by using a compact representation. Another way to think about this is the database is certain and the query is uncertain. So when the user says Madison SQ NY, he means any one of these 4 queries, which says that when he says SQ, he could mean SQ or he could mean square. Okay? When he says NY, he could mean NY or he could mean New York. So now the relation is certain, but our query is uncertain. Okay, so conceptually taking a union of all these results is the same as the previous slide semantics that I defined. So in general, this notion of transformations is extremely powerful. The reason is it can capture similarity which is not captured by any textual method, for instance, or it can capture similarities which may not be amenable to doing in the set containment world or in the set similarity world, right? So this essentially lets us program similarity functions by just creating conceptually a relation which basically keeps information about synonyms. Okay, so what we have is two kinds of error tolerance in this problem. Yes?
If you're treating the transformation as synonyms, then couldn't the uncertainty also be in the reference relation?
Yes, so conceptually, okay, so we don't treat them as synonyms, these are one-way things. You can conceptually have transformations applied to both the query side and the reference relation side. And so, yeah, so that is a valid question. In this talk, we'll keep things simple and do it only on one side. So now, yes.
So I have a question. So let's say that in the simple case where there's no transformation, they're just doing Jaccard containment over, let's say, large data set.
Right.
Is this problem efficiently running this Jaccard containment over large data set? Is this problem well solved? Or?
So this problem, there is a solution for that part of the problem called prefix filter. Our solution, as you'll see, will be more efficient than that solution. So yeah, even Jaccard containment without transformations is a hard problem, and our solution will essentially improve on that problem while also solving the transformations case. That's a very nice question. Yes. Okay. So, and the experiment slide should show that, and if not, please ask me again. So now let's try to do Jaccard containment without transformations for a minute and see how one way we might be able to solve it. So we have a query Madison SQNY, and we'd like to do a Jaccard containment with threshold of 0.6. What this says is at least 0.6 part of this query should be covered by any record that is in the answer. Hence, one thing we can immediately see is if we issue these two red queries, Madison SQ and SQNY, both of these have weights which are greater than the threshold, and get the results and union them, that is the correct result. And the reason is, for anything to cover more than 0.6 of the query, it has to cover at least one of these two. Is that clear? Because if we only had a query which was Madison NY, that's only 0.5. So we don't want to issue those queries. On the other hand, if we try to issue the entire query Madison SQNY, the answer there is a subset of the answer of any one of these queries. So we'll get all of those answers. So we'll get all answers with threshold of either 0.8 or 0.7 or 1. Those are the only three values you can essentially have Jaccard containment for this. Okay? So essentially to issue a Jaccard containment query without transformations, we can find a collection of set containment queries, which on unioning we can get a Jaccard containment answer. Okay? And this is how that's done. In the presence of transformation, this generalizes nicely. You apply conceptually the transform query, the green one. For that, again, do the same process of finding queries such that you can answer that. Now by taking all of the transformed, all of these red queries, so you generate all transformed queries, the green ones, by applying transformations. Then you find their subsets as I defined earlier, and you take all of these red queries, issue them, take their union, and now that is the exact result you would like for Jaccard containment in the presence of transformation. So this is conceptually one naive way of doing things. Of course, you can see that there is a large explosion here. The red queries are what we will call variants in the rest of the talk. These are variants of the query which are set containment queries whose union is the exact answer for Jaccard containment with transformations. Okay? So this tells us a naive solution outline, which is you're given a query, generate all of its variants which are set containment queries. For set containment queries, we know inverted index work well. Use an inverted index to answer each of these queries, get their results, do a union, fetch those from the reference relation. The union essentially gives you IDs, fetch those from your reference relation and get the result. Okay? So this is a system that can be easily built using this naive intuition. What are the problems with this naive solution? Why is this naive? There's one, too many variants. The number of transformed queries can be exponentially large because it's essentially a cross product. Secondly, each set containment lookup itself can be very expensive when we are having to do a lot of them to answer one request. So if we had to do only one set containment lookup, it is efficient enough. But when you have to do a large number of them, we want to optimize that part as well. One reason why it can be very expensive is, think of a query which is Madison NY. Okay, both of these are cities, so their lists are fairly large. There's a lot of local places in Madison, there's a lot of places in NY. Their intersection might be really small, which is things like Madison Square Garden, for instance. So the intersection, to do an intersection of two very large lists is too expensive to get a very small result. So in this, we'll attack both of these angles. First, let's see intuition as to how we might not have to issue all these large number of variants to solve the problem. So there's intuition for issuing fewer number of queries. This says, so again, the yellow was the original query, the green one is a transformed query, the red ones are the variants. So we'd essentially conceptually like to issue all variants to answer our query. Think of a blue query which is Madison. This arrow denotes that this query result contains all the results from these two red queries. Okay, because if you have fewer keywords, you get more results, a union of results. So now by issuing the blue query, we are sure that we get all the results from those two red queries. Similarly, by issuing this other blue query, the NY, we get those two. So at this point, we can notice that by issuing these two queries, we'll get a superset of all results for all the variants. And this is what is called a variant covering. Notice that fewer queries are issued possibly by doing a covering, but you can get false positives. There will be results which you will get by issuing both of these queries that are not results in any of those four queries. Okay? So by issuing fewer queries, we might be able to get more results, which is sort of a trivial statement, because by issuing the empty query, you get the entire database. Right? So an empty query is always a variant covering. Okay? So we'd essentially like to find nice variant covering, and there are many of them. There's another variant covering square or SQ, there's a variant covering with 3 queries here. So essentially the problem is of finding a good covering. So what this indicates is a solution outline, which how we might be able to change and improve it. One, as I hinted earlier, we are going to improve on the inverted index to make it more efficient for doing set containment queries by introducing something called a minimal infrequent index, which is a more efficient version. The second part will be doing an algorithm called covergen, which will generate good variant coverings efficiently. The intuition is that we want to issue fewer queries because we can't issue an exponentially large number of queries. And a third part is, now we'll get a superset of the results. So we have to do this additional step of verifying which are the correct results. Okay? Because we are using a variant covering, we need to do this final phase of throwing away results which actually don't exceed our Jaccard containment threshold. For this third part, there's an algorithm in our paper which uses maximum matching, which I'll not discuss at all in this talk. That algorithm essentially tries to say, given a record and a query, is the Jaccard containment greater than this threshold, and does this efficiently. So first let's talk about our minimal infrequent index. In our minimal infrequent index, one intuition is we are not only going to create lists for individual keywords. We are going to create lists for sets of keywords as well, which can be thought of as queries. So instead of just having 4 lists for each of these 4 keywords, you could have a list which materializes the result for the query Madison NY, which is for a set. Okay? But we are not going to generate all of them. We are going to be smart about that. So what we'll have is a parameter A, and say that we have that's a frequency threshold, which says that any list longer than size A is too frequent, okay, which will not index. So what we'll do is, we'll not index long lists, which are longer than this parameter A. We'll only index lists smaller than A. In addition, we'll only index lists which are minimal among these infrequent lists. So for instance, we'll not index the list for Madison Square NY because there is already an index part which is square NY, which is small enough that, and it contains all the results in Madison Square NY. Okay? So we'll index minimal infrequent sets or minimal infrequent queries for a threshold A. Okay? So notice that we only index like 3 of these lists in this index, for example. Now how is this index useful? Think of first only queries which have fewer than A results. So think of a query such that we know it has less than A results in its output. For this query, what we can do to answer this is find, by definition there is a minimal infrequent set that we have indexed which contains this query. We can find that, we can fetch all of those records which are less than A and verify whether or not they actually satisfy the query and create our answer. And this example sort of says that Madison square NY was our query and Madison square is a list we have. And we are able to answer this query by finding first quickly which this list is, and secondly just scanning this list and verifying each record in this list. Now when we have queries with more than A results, you can think of an exponential set of parameters A, 2A, 4A, which you can all overlay in the same index. And then now a query conceptually which has between A and 2A results will be answered by the 2A index. A query which has less than A results will be answered by the A index, and so on. Okay? So what this says is, if a query has O results, if this O is greater than A, then or greater than A by 2, we are going to do it in at most 2 times the number of results. But if it's like 0 results, we still need time A to make sure that it has 0 results or less than A results. So we have an output sensitive guarantee for doing set containment lookups. Okay? So this is the index we will use for our set containment lookups in our solution. The index will be useful in other ways as well, because the index has metadata which is about frequency of various queries. So since we've materialized queries other than just singletons, we have more knowledge about how big the results are, which we'll use in our cover gen part of the paper. But also this index itself, which has an output sensitive guarantee for set containment, is of independent interest, because it provides essentially a trade-off in between space and efficiency. You save on query time, obviously you index more things. So we've seen the minimal infrequent index for efficient set containments. One observation, yes?
Just quickly on this index, so do you make any implicit assumptions on the way the data has to be distributed for this index to be applicable?
The index always applies. The size of the index can really blow up.
To be realistically applicable.
So, okay, so if you have sort of small, if you have small records, index is usually small. If you have large records, the index can get large as defined. But another thing to note is this index, if defined, I used a definition of index which is frequency based. You can use any monotonic function over instead of just a frequency function. So you can essentially, and that can be used to control the size of your index. For instance, if you have long records, one thing we spoke about in the paper is 2 things have to be close to each other within some distance for them to be co-located in our index. So our frequency threshold, or you can say things like the biggest set we will ever materialize has 3 keywords in it, and we will not do 5 keyword sets. So you can essentially choose for various settings different monotonic functions to control the size of the index. We also did some investigation about how big the index would be for general data, and there is evidence in the frequent item sets literature to suggest that the index is usually small, because not all permutations occur frequently. Okay, it's the same intuition as why a priori algorithm is usually efficient. It also generates all of these sets. In fact, it generates way more than the minimal infrequent sets. But yes,
you still need the original index of single borders, do you?
We don't need it per se, but our index is essentially a superset of that. We will definitely, so think of it this way, since we have an exponentially large number of parameters, think of any individual keyword and its list. Its frequency has to lie between 2 of these guys. So it will be minimal infrequent for one of them, for something, right? Hence that list will be materialized for one of these. So an inverted index, our index contains all the lists that are in the inverted index plus more. Okay. Another observation to make is when we use a parameter of a equals infinity as the lowest parameter, the index is the inverted index. So our index for a certain parameter value is exactly the inverted index, just because every individual keyword is minimal infrequent for the a equals infinity case. So we had a question about index size. We don't really make too many contributions about index size in build. We basically use literature from frequent item sets to do our index build, and we have arguments to support why the index is usually small and tools to enable that. So the next part is, how do we issue fewer queries? How do we generate this cover which is good? There are two things which are challenging here. One, we don't want to verify too much. We don't, like, one covering would be the empty set, hence get the entire database and verify it. That's too inefficient. We don't want to spend all our time in conversion as well. So there are these two things we want to optimize for. As I hinted earlier, the information from our index will help us will feed into how we do our conversion. So the index, we can sort of have metadata which says that this query has this many results instead of just for singletons. So we essentially have the frequency diagram in some sense of our data. Now one approach, which is the obvious approach, is the set cover approach for generating this covering. Let me try to formalize what this problem is. So we had a query, a threshold, a bunch of transformations, and we were able to generate our variants from this set. Given these variants and given list that we have, so we have a parameter A collection, we have a parameter 2A collection, we have a parameter 4A collection, and this is all our index. Okay? Given this, we now know also the length of all of these lists. The question is, can we cover? Now Madison covers the first two queries. Madison square covers only the first query, and square covers the middle two queries, and so on. So this is a set cover problem in the sense, can we cover our variants using some list that we have? So the cost for each set is just the length of that list, because we are going to fetch all of those and verify against them. So this, I'll argue, the blue set here, the three middle queries, is a variant covering because it covers all of our variants. Okay, that's kind of redundant, but so the thing is that we can, by knowing the cost from our index. Yes.
But the cost is just the verification cost, but you also have the cover gen and the index lookup cost. Right? Is that also covered in the?
No. So okay. So the formal guarantee. So this cost metric is for defining what's a good cover. Is this, so this cost is essentially only measuring the goodness of our covering in terms of false positives. How many false positives will you get as a result of using this covering?
But false positives is not the only thing, right? I mean, there are other two aspects, the cover gen and the index lookup.
Absolutely, and that's why I'll say that set cover is not a good solution, and I'll give you an alternative one. So,
but if you plug in that cost function there, which includes all these costs, then maybe you can do something else.
So that's possible. So the way we went about this is we are trying to get a good quality covering, and we're not accounting for how efficiently you generate this covering. It's like saying in optimization we want a good plan, but for now we are not accounting for how expensive it is to compute this plan. Okay, think of these blue things as a plan. So the cost as we are implementing it is exactly the verification cost modulo overlaps for these. But so recall how this is going to work. We are going to take all of these lists, collect these IDs, fetch all of these records, which is again linear in this cost. For each of those records, run the verification algorithm. So the cost after generating the covering is proportional to the cost I have here. The cost of generating the covering is something I'm not measuring in defining this. Okay, and that's actually where the set cover algorithm will essentially have its downside. Okay.
Cover gen like a dominating portion of the cost? Or?
We'll see that in the experiment. That's an excellent question. Our experiments will show a difference in where the cost goes. So okay. So to recap, we can now, using metadata from our index and a greedy set cover algorithm, generate a variant covering which has from set cover a guarantee that you're not getting too many false positives. There's a bound on the number of false positives you will get as a result of doing this. So set cover has this nice property which is a bound on false positives. You will not unnecessarily verify a lot of things. The problem with this, as was noticed, was that generating the covering itself may be expensive. Since I said there's a large number of these variants possible, in our set cover algorithm we are having to generate all of these large number of variants and then run a set cover computation over them. So the set cover instance itself is very large, and hence this might be too expensive to generate, especially in the presence of a lot of transformations. So to that end, we have an alternative solution, which is what we call the hitting set approach, which essentially I'll not talk about in great detail, but here's the intuition. It essentially generates a covering, which is this blue things, which is this blue query to issue set containment to the set containment part, which without actually enumerating all the variants. So we can guarantee that we will cover all our variants without ever generating these variants. And this uses essentially work from monotone dualization or lattice theory, which was specially applied to frequent item sets to essentially indicate how this was done. This intuition exists in existing literature. But one thing that's interesting is that we require our index to have this property that it's enumerating all minimal infrequent sets for this algorithm to work, because it does basically walks on this lattice going up and down, and it has to hit a border. Okay, so another thing to note here is while the variant covering may be generated more efficiently than set cover, it's heuristic in the number of false positives. So set cover had this nice guarantee that we have a theoretical bound on the number of false positives we will have. Here that bound no longer applies, it's heuristic, but in our experiments we'll see how that affects us. So this was the second part of the second approach, which essentially addresses the problem of generating the covering itself efficiently and not only looking at false positives. So to set up the one experimental result that I'll show you, we had a prototype implementation as a standalone library. It uses an in-memory index as you'd expect. So we used a bunch of data sets. The experiment I'll show you is from a places data set, which is probably similar to the motivating example we've been running through. It has 7 million records. To talk a little bit about the transformations we had in this experiment, we had up to 20 million transformations in different experiments. These experiments could be static, which are of the form that Bob is Robert or SQ is square and so on. These are applied, so there's a small number of these. Then there's a large number of these programmatic transformations like edit distances or abbreviations. Edit distances are everything within edit distance of 1 or 2 of a word, or abbreviations are A could go to Alex or J could go to Jack, John, Jim, whatever. These are programmatically provided. These are not like materialized in a table anywhere, but programmatically provided at query time. The experiment I'll show you is to compare the hitting set approach with the set cover approach, and we'll see the time split as to in the various parts of the thing. To compare to prior work, unfortunately no prior work, or fortunately no prior work handles the problem of Jaccard containment with transformations. As we mentioned, there's prior work called prefix filter, which handles the Jaccard containment case alone without transformations. One observation you can make is our hitting set algorithm can degenerate if you don't have transformations to this work. Secondly, our index, when you use the parameter a is equal to infinity, can degenerate to the exact index that prefix filter uses, which is the inverted index. So we can essentially, using our implementation, implement prefix filter directly, and this is what we will compare to. Okay, so also this gives us a natural way of saying how does prefix filter generalize to the case of transformations. We use it, our implementation, with transformations over the index a equals infinity. Okay, so this is the plot comparing this. There's a lot of setup here. On the x-axis we are sort of changing the amount of transformations in the 3 sets of plots. Each set has the 3 algorithms I've been mentioning: the prefix filter, the hitting set, and set cover. On the y-axis we have performance. Lower is better, quicker. So the 3 colors represent parts in various parts of the algorithm. The cover gen is the red part, and the lookup, fetch from the index, and verify is the yellow, gold, whatever part. Okay, and the overheads are the green part. So one thing to note for all these 3 sets of plots is that the first plot uses less memory than the second and third, because it uses the regular inverted index, while the second and third part use our minimal infrequent index, which for this data set had a 20% overhead. Okay, so we're comparing performance, but there is a memory difference between the first part and the second and third part. So now let's see what these results say. So when you have no transformations, by just the gain from using our index is essentially a 3-fold improvement in performance, And the hitting set and set cover algorithm are essentially, since there's not a very large number of variants in general, just because of a Jaccard containment threshold, we don't see the difference. So they're essentially similar. One thing this says is that the hitting set heuristic worked well in this case. As we increase the number of transformations, everything becomes slower, which is kind of expected because there's now a larger number of queries you want to issue, more error tolerance, more results. But as the transformation becomes really large, you start seeing in the set cover, the red part blows up. So the set cover, generating the cover becomes very expensive at that point. Okay? And the hitting set has a significant benefit in when the number of transformations are large. Also, you'll notice that the hitting set index plus verify part is only a little bit more than the set cover. So while heuristic, in practice for this experiment it was not bad, the generated covering in terms of false positives, yes.
To which degree do these numbers rely on the fact that your index is in memory? So if I have a disk-based index where sort of navigating to the start of the posting list in your index becomes suddenly relatively much more expensive, how would these things change, and can you adapt your algorithm to this?
Okay, so let me repeat the question to see if I got it. So if our lists were resident on disk, there's an overhead of getting to the top of the list.
Yes.
And so the question is, how does our algorithm vary relative to the others? It's a good question. So I would say that our algorithms would actually become less efficient in this case, because if you look at the inverted list, there's a keyword, there's a query, and there's transformations. So there's a set of reachable keywords from those queries, which is a small set, which is in the size of the query and the number of transformations you have, linear. So if you have 10 transformations which go to different endpoints, you have these 10 plus 5, 15 essential keywords to look up. You can essentially collect all of them and sort of do work in memory in some sense to get the answer. So the inverted index solution touches fewer posting lists. Our solution touches far more posting lists than this. Hence, from that point of view, if you put it on disk, my intuition suggests that our solution will become less efficient, because it's just having to touch just more number of lists. But how this, so there's two opposing factors. My guess is that the prefix filter will sort of win. Okay. Yes.
For understanding, how many words do you have in the experiments here?
Query words?
Yes. Or unique keywords which you indexed or query words?
I actually do not know the answer to that question. So yeah, I do not have an answer. Does Raghav know? How many distinct words in the whole collection? Like inverted list, how many lists would it have? Okay. Yeah. Thanks, Raghav. So the conclusion of this experiment was that the hitting set, when there are large number of transformations, can help significantly, and the heuristic index, the verification that happens, it's not too bad. Again, as before, there's a lot of related work that draws into this. There's work in similarity functions, fuzzy lookups have been defined for various other things. There's obviously inverted indexes and lift intersection work. There's work from fuzzy autocompletion which is relevant. Obviously we used a lot of work from frequent item sets mining, and maybe more that I forgot to list here. So we've seen two main parts of our talk. Now let me give you one slide overviews of the trendy topics part to promote discussion. The first one is, how do you do SQL inside what people are calling NoSQL systems? So we started with a NoSQL system called Peanuts, which is essentially a data store for serving web content. What this system does is range scans and point lookups. And the key ingredients of this system are, it works at a very large scale, horizontal scalability, very low latency for web serving. It does geographic replication to do low latency across, like for workloads which are global. It does weak consistency guarantees at a per record level rather than across record coordination. The system is designed to be highly available, very fault tolerant, thinks about a bunch of failure modes, tries to make sure that the data stays and performance is not very affected in terms of various kinds of failures. What we did was we added this notion called replica views, which essentially enable you to do richer set of SQL on this rather than just these simple functionality, which is secondary access, simple joins, echo joins, some group by aggregates. So there's a lot of fine print as to what part of SQL you can do. You cannot do ad hoc SQL. You can do only pre-declared SQL, and you can only do restricted SQL. But we claim that those are the interesting parts for web serving. I'll not go into the fine print and just leave you with the good stuff. And the key idea was replica views, which helped us not have to worry about keeping all those scale by treating our views as peanuts tables, the same way as replica peanuts tables were treated. We are able to borrow all the same consistency abstractions. We are able to get the whole geographic replication. We are able to get the fault tolerance. So the cool idea was, by just reusing and conceptually thinking of our views as replicas, which are just accessed differently, you get a lot of the benefits in terms of abstractions and engineering. Okay, so this was this work I did with Yahoo. A second one was to share scans in a MapReduce like system. So the context was that Yahoo has a Hadoop cluster with a bunch of data sets, some of these very large. Pig sits on top of this, and there's queries hitting all of these data sets continuously. One observation is a large part of the time spent by this system was spent analyzing a few very popular data sets, which suggests that there's a bunch of queries attacking the same data sets. So there's an opportunity to share work across these queries. So one scan can sort of answer multiple queries or help answer multiple queries. So that's the opportunity. The way we went about it is we modeled how to anticipate these query arrivals, because essentially to do this sharing you have to make one query wait while another one arrives which it can share with. So by anticipating query arrivals, we were able to build a priority based scheduler which can help you do this scan sharing to enable efficient computation of our big queries. The challenge there is that this increases throughput while possibly decreasing latency. So our contribution was to define a metric for how to share scans, because in theory you can just make everyone wait for a long while and you get more sharing, so conceptually more throughput, but the latency increases. Okay, so we defined metrics for saying how to do this scan sharing, and we had a paper about that in VLDB. So now I've spoken about the two parts in detail and two parts just one slide overviews to promote discussion. Let me just throw up a bunch of other work that I've done. I'm currently working with folks at AT&T on a data mining problem, which is how do you summarize databases. I've done a study group essentially to make a case for RAM clouds, which is essentially a peanuts-like system for, except the twist is that all your data is in memory. It's still durable, but it's always served from memory. And this introduces a bunch of challenges and a bunch of opportunities. And we essentially had a study group to figure this out, and we made a case for RAM clouds with a large number of people at Stanford. I've done a bunch of other work on uncertain data, which is not about integration but core uncertain data. So with that, let me throw up a list of my co-authors over the last few years. I've worked with people at Yahoo Research, Microsoft Research, AT&T Labs, Stanford Computer Science outside of the InfoLab, and a bunch of people at InfoLab. I'd like to thank all of them as well as you guys for attending. Thank you very much. And I have a minute for questions.
One question, we'll take that. Otherwise, we'll just stop here. I think we'll stop. Let's thank the speaker again.
All right.